Hello, my name is Mohammad Zaki Khan and today we are going to discuss fourth question of the first internal. The question is state true and false. First statement, minimize the number of arithmetic operations whenever possible. This statement is true because there are several reasons why it is beneficial to minimize the number of arithmetic operations whenever possible. First, efficiency. Performing arithmetic operation is a computational expensive process. By minimizing the number of operations required, we can improve the efficiency and reduce the processing time. Accuracy. Each arithmetic operation introduces a certain degree of error which can accumulate over multiple operations. By minimizing the number of operations, we can reduce the overall error and improve the accuracy of result. Robustness. Arithmetic operation can also lead to numerical instabilities and divergence, especially when dealing with a large or small values. By minimizing the number of operations, we can reduce the risk of numerical instabilities and make algorithm more robust. Overall, minimizing the number of arithmetic can lead to more efficient, accurate, and robust algorithm with lower memory requirement. Avoid Avoid taking the difference of two nearly equal number whenever possible by alternate formulation of problem. If it cannot be avoided, then take difference before doing other operations. This statement is true because taking the difference of two nearly equal number can lead to the loss of accuracy in numerical instability, especially when dealing with floating point arithmetic. This is because the difference between the two nearly equal number can result in very small number that may lose due to limited precision of floating point arithmetic. For example, consider the subtraction of two nearly equal numbers. A equals to 1 point this much zeros 1, B equals to this C, and we are performing a subtraction for these both numbers. In this case, the value of C is very small and may be lost due to limited precision of floating point arithmetic. This can lead to inaccurate results and numerical instability, especially if C is used in a subsequent calculation. To avoid the problem, it is recommended to use an alternate formulation of problem that avoids taking the difference of two equal numbers. This can involve algebraic manipulation of recording of calculation to reduce the sensitivity to small changes in input. If it is not possible to avoid taking the difference of two nearly equal numbers, it is recommended to take difference before performing other operation. It can help to reduce impact of loss precision and improve accuracy of result. Overall, avoiding the difference of two equal number and taking difference before performing their operation can help improve the accuracy and numerical stability of all algorithm can involve floating point arithmetic. Now moving to third statement, adding or subtracting numbers starting with smallest number and work with number in ascending order. This statement is true because adding or subtracting numbers starting with smallest number and working with numbers in ascending order can improve the accuracy of numerical stability of calculation. When adding or subtracting numbers with different magnitude, it is important to start with smallest number to reduce the impact of a limited precision of floating point arithmetic. This is because small numbers have fewer digits and are less effective to rounding error than large numbers. By working with numerical in ascending order, we can also reduce the accumulation of rounding errors and numerical instabilities. This is because rounding error can accumulate more rapidly when adding or subtracting large numbers, while small numbers are less sensitive to these errors. For example, we have given A, B, C, D as floating points. If we add this number, we get result 46.9035. Fourth statement, do not formulate an algorithm that tests whether a floating point number is equal to 0. True, it is not recommended to formulate an algorithm that tests whether a floating point number equals to 0 because floating point number are not exactly their values and may be subject to rounding error. Due to the limited precision of floating point, arithmetic is difficult to represent certain number exactly including 0. This means that even if floating point numbers are mathematically equal to 0, their representation in memory may differ due to rounding error. Instead of testing whether a floating point number equals 0, it is better to use threshold or tolerance value to check whether the absolute value of 0 is sufficiently small. In the algorithm, is the floating point number being tested and epsilon is tolerance value. The f's function is used to get absolute value and function returns true if the absolute value is less. Using this for epsilon, we can handle floating point number more accurately and robustly than testing exact t equals to 0. Ill conditioning of problem is normal due to improper formulating and can be eliminated by carefully reformulating the problem. A practical way is if detect suspected ill conditional is alter the parameter by small amount and observe their effects of solution. This statement is partially true because ill conditional of problem can be improper formulation, but it can also be due to the nature of the problem itself. Ill conditioning means the small checking in the input or parameter of the problem can lead to large changes in the output of the solution or makes problem difficult to solve accurately and can lead to numerical instabilities. One way to detect suspected ill conditional conditioning is indeed to alter the parameter by a small amount and observe their effects on the solution. This is known as sensitivity analysis. By analyzing the sensitivity of solution to change the input parameter, we can determine whether the problem is well conditioned or ill conditioned. If the solution is highly sensitive to small changes in the input, then the problem is likely to be ill conditioned. However, simply altering the parameter by a small amount may not always be enough to eliminate ill conditioning. In some cases, a careful reformulation of problems may be necessary to improve its conditioning. This may involve changing the formulation of problem, introducing additional constraints or assumptions, or using a different numerical method of algorithm.